1. Opening. A healthy world, then not. Before the dinosaurs, Earth looked very different. All the land was gathered into one giant body, Pangaea. The supercontinent stretched from north to south. Fewer coastlines, harsher interiors, seasons that could be brutal. The seas were not like the Cretaceous, but they were alive. Ancient corals, unlike anything today. Brachiopods, drifting plankton, armored fish, deep water hunters. On land, it was a world ahead of the dinosaurs. No T-Rex, no raptors, no Jurassic Park chases. Instead, there were therapsids, the mammal-like reptiles. Not fully reptiles, not yet mammals. Some big plant-eaters, some fox-sized hunters, some wolf-like ambushers. Forests were conifers, giant ferns, drought-tolerant plants. In short, ecosystems were already complex. Life had diversified, and then the planet was almost reset. About 90 to 95% of marine species disappeared. Around 70% of life on land didn't make it. Ancient reefs collapsed. The signature Permian creatures vanished from the record. Geologists call it the Great Dying, so the question is, what is big enough, long enough, and toxic enough to kill almost everything? 2. What were the Siberian Traps? Picture this. A region the size of millions of square kilometers in what is now Siberia, slowly buried under sheet after sheet of basaltic lava. Not a single volcano glowing once, but long fissures, opening, pouring lava sideways like black cement. It didn't erupt and stop. It erupted, rested, erupted again, rested, again. Every pulse laid down a new page of rock, layer on layer, step on step. That's why we call them traps, stair-step basalts. But the problem wasn't just a lot of lava. The problem was where it erupted. The magma rose through rocks rich in coal, organics and carbonates. And when superhot magma cooks those rocks, it releases a vicious cocktail. Huge amounts of CO2, driving global warming. SO2, creating acid rain that punishes forests and shallow seas. Methane, CH4, from sediments and maybe from destabilized clathrates, pushing the greenhouse even harder. And halogens, chlorine, fluorine, that may have damaged the ozone layer, letting more UV strike the surface. This wasn't just a volcanic event. It was a climate event, a chemical event, and an ecological event, all triggered by fire from below. 3. Cinematic entry, when Earth could not breathe. This was not a single spectacular impact. This was a long suffocation. Earth was not punched. Earth was smoked, not for hours, for thousands of years. Lava fountained, rivers of fire crawled across the ground. Hot gases punched into the upper air. Ash and sulfur drifted outward and began to build. A dirty atmosphere. At first, the aerosols and SO2 may even have cooled parts of the planet by blocking sunlight. But the CO2 and methane kept coming, and they kept coming, and they kept coming. So the long-term direction was only one way, hotter. Not by half a degree. Some models suggest surface oceans warmed by 6 to 10 degrees Celsius, even more near the poles. A warmer ocean holds less oxygen. Less oxygen at depth means more room for anaerobic microbes. Anaerobic microbes make hydrogen sulfide. Hydrogen sulfide turns parts of the ocean into toxic sulfidic water, what we call euxinic. A warm, breathless, poisonous ocean is a death sentence for most marine life. 4. How does an ocean die? Let's go step by step. First, heating and acid rain. On land, acid rain burned forests and topsoil. Trees weakened, roots damaged, leaves lost. Soil was no longer held in place. Erosion spiked, and everything eroded. Mud, nutrients, even metals, was flushed down rivers into the sea. Second, surface overfeeding. All that nutrient input triggered plankton blooms at the surface. Blooms die. Dead plankton sinks. Microbes eat the dead plankton. Microbes use up oxygen in deeper water. Anoxic zones grow. Third, anoxia spreads. When low oxygen water covers the sea floor, bottom dwellers die. Ancient corals, brachiopods, any attached, slow, fixed animal They cannot run. Bottom without oxygen means bottom without life. Fourth, hydrogen sulfide joins the party. In oxygen-free water, sulfate-reducing bacteria thrive and produce H2S. Hydrogen sulfide is extremely toxic to most aerobic life. If this sulfidic deep water wells up to the surface, or if H2S escapes into the air, it can hit surface ecosystems like a silent bomb. Some hypotheses even say H2S in the air plus a damaged ozone layer means even nastier conditions at the surface. Fifth, the food web unravels. With the seafloor gone, the middle water stressed and the surface unstable, filter feeders, bottom feeders, slow reproducers, they all lose. Fossils show whole groups that were already in decline simply vanish. Ancient coral styles, gone. Certain trilobite lineages, gone. The ocean did not die with a bang. The ocean died with silence. It stopped giving oxygen. It stopped carrying food. It stopped being the sea of life. It became a warm, black broth. 5. What about the land? Don't forget, the Permian Triassic extinction was not just a marine disaster. The continents burned too. Forests collapsed. In the layers right around the boundary, plant remains drop and fungal spores spike. That fungal spike is like a crime scene photo. Forests died. Dead organic matter piled up. Fungi feasted. Spores exploded. And when fungi thrive, everything else is struggling. Land animals were hit 3 ways: heat, toxins, and hunger. In the middle of Pangaea, temperatures may have become brutally high, too high for many animals to regulate their bodies. Acid rains stripped food plants. Volcanic gases, and maybe H2S from the oceans, made breathing harder. The big therapsids, the ones with long food chains behind them, the heavy-eating ones, they were selected against. Who survived? The small, the hidden, the generalists, the burrowers, the low-maintenance species. That is the survival pattern after every great catastrophe. A medium-sized therapsid walks through a ruined grove. The trunks are black, the leaves are gone. The sky is not storm grey, it is volcanic brown. The animal stops, it breathes, it coughs, and the cough of something 252 million years old sounds tired. 6. Time, the hidden villain. Unlike the KPG impact, one day, one rock and then fallout, the Great Dying was a sequence. Studies suggest the extinction came in pulses, tens of thousands of years apart. Life tried to get up, and another wave of heat or acid or anoxia knocked it back down. That is what made it so cruel. It was long. Ecosystems need time to rebuild, to reweave food webs, to repopulate empty niches. But every time the weave began, the furnace in Siberia turned back on. It's like being in the hospital, and someone keeps switching off the oxygen. Life can rise after tragedy. Life struggles to rise, when tragedy will not stop. 7. Why call it the Great Dying? Because it didn't just kill individuals, it erased options. It narrowed evolution. After the boundary in the early Triassic seas, life looks poor. Fewer coral styles, fewer attachers, fewer weird body plans. On land, the big, swaggering apex therapsids are gone, and the door is open for agile opportunists to move in. And that empty space, that is what later allowed the dinosaurs to dominate. If the Permian Triassic extinction had been softer, maybe those earlier reptile-mammal forms would have stayed in charge, and the age of dinosaurs would have been smaller, quieter, or never quite the same. So the Great Dying was also a great clearing. A rotten forest burned away, so something new could grow. 8. Making the climate feel cinematic. To tell this in a cinematic, realistic style, the air has to become a character. Sky colors should step down: blue, acid yellow, sick orange, brown gray. Light should feel as if it passed through a dirty filter, aerosol light, not golden sunset. Sound should be low and constant, the rumble of a hot earth, distant volcanic throats, hot wind. Little details sell it. Leaves pitted with tiny acid holes, white crusts on the ground from evaporated salts, puddles with a purple-green bacterial skin because there's no oxygen. This was not hell, because hell is all flame. This was worse, a planetary smelter that no one turned off. 9. The toxic edge. Sulfur, halogens, ozone. One reason this interval is terrifying is that the gases didn't just heat, they hurt. SO2 lofted high, acid rain, nutrient washout, plant collapse, herbivore collapse. Halogen-rich emissions, possible ozone thinning, more UVB at the surface, damaged spores, damaged pollen, damaged embryos. In rock records, some pollen looks malformed, like it tried to grow under stress. That's a fingerprint of a sky gone harsh. Not everywhere was equally bad, but the message is clear. The air was no friend. 10. The important point. It didn't end in a day. We love stories that go boom. The Great Dying went still going. What made it lethal was length plus layers. A giant volcanic outpouring, greenhouse gases and SO2. Acid rain, erosion, nutrient dump, anoxia. Warming, oxygen loss, anaerobes, H2S. H2S plus weak ozone, toxicity on land. Soil, forest, and sea all sag at once. Mass extinction. If you want to tell it on video, split it. 1. A planet before fever. 2. Siberian Traps. The furnace opens. 3. Oceans suffocate. 4. Forests fall. 5. Life restarts. 11. Who made it through? Not everything died. The winners were small, flexible, low-demand creatures. Burrowers, omnivores, things that could hide, slow down or wait. Some conodonts hung on. Some large amphibians persisted in the right places. And crucially, small reptilian lineages, the ones that would become archosaurs and much later dinosaurs, crossed the bottleneck. So yes, the Great Dying did not reward the strong. It rewarded the modest. The Great Dying did not favor power. It favored those who could ask for less. 12. Lesson for now. We don't look back 252 million years to scare ourselves. We look back to see what Earth systems can do when they are pushed. Rapid greenhouse gas rise, warmer, oxygen-poor oceans, weakened land ecosystems. We know this pattern. We are talking about it today. The difference? Siberian Traps did it with magma. We are doing it with industry, deforestation, and fossil fuels. Different source, similar direction. Earth once fell terribly ill. It recovered, but it took millions of years. Life returned, but not the same life. We are here because the table was cleared once. That makes us lucky and responsible. If one long volcanic outbreath could make the ocean stop breathing, we should be careful with what we are pumping into the sky now.